Here we are back on the bench with the 8-bit computer. This time we're going to be going through this program that computes the Fibonacci series step by step. First we're going to look at the assembly instructions and a teardown of what they're actually doing. Then we're going to go through entering them into memory, and then finally stepping through the execution.
Okay, so I've written up this program here in the RMX language for Robert Mead Assembly. It's going to run on the 8-bit computer to generate Fibonacci numbers, and I'm just going to go through it here with a pen, mark it up, and we're going to go over what it does. So the Fibonacci series is defined pretty simply as starting with these two numbers, f0, which is 0, and f1, which is equal to 1. Then it's defined such that f of n plus 1 is equal to f of n plus f of n minus 1. So if we're calculating f of 2, for example, is equal to f of 1 plus f of 0. So this is just, in general, how we define the Fibonacci series. And then we'll see if we start with 0 and 1, we add these two together, 1 plus 0 to get f2, which is 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 5, 8, and we just keep going. Okay, so the way that this program actually executes is pretty simple. We're just going to carry two variables through the whole time, starting with f1 and f0. Let's just call them A and B so we don't get confused, where A is going to be the current Fibonacci number and B is going to be the previous Fibonacci number. So what we're going to do is add them together, calculate the next Fibonacci number to be the current, and then we're going to subtract back to get the previous and output the previous. And we're just going to do that through iteratively. So from a numbers perspective, it's going to look something like this, where we start with A being our f1 is equal to 1, and B being our f0 is equal to 0. Then to calculate the next index, we're just going to combine these two, add them together, and then that's going to go to A, such that A becomes the new current, and 1 plus 0 is 1. And then we take back the value we have, the A, and we just subtract 0 from it to find that A minus B, which is 1 minus 0. So we do a subtraction here, and we find that B is equal to 1. So now we have our next two indices, and we repeat the process. After we take these two together, we add them, and we get A is equal to 2. Then we take these two together, and we subtract them, and we get B is equal to 1. And this goes on for a little bit, and then we go through and we get a 3 and a 2, and then subsequently a 5 and a 3. And the whole time that we're going through this, we are outputting the previous. So we start with the 0, then the 1, then the 1 again, then the 2, then the 3, in that order for our output. And that's exactly what this assembly does here, where we're just going to go through, and in the assembly language, the first thing we do is we initialize our A is equal to 1. Then we initialize that our B is equal to 0. Well, I should say we do this, yes. Then we initialize our B equal to 0 here. Then the next thing we do is we do our first output instruction. So this is out previous right here, where we output the contents of the A register. Then we calculate the next one and store that. So let's just do that in blue, where we add the contents of the previous and then we store it back where it was. So this is calc next. And then after we calculate the next one and store it, we calculate the previous one and store it. So we calculate the previous, and then if we're done, this is a reset right here. So if we need to reset the program, we just go back to the beginning. And if we are not resetting the whole program, then we end up doing this unconditional jump down here at the end, where we're just going to go from here, which just does a jump. And this jump right here goes back to instruction 6, where it outputs. Keep going. And we go through all the numbers until we hit one that results in a negative 2's complement value. So we'll get through to 89 before the sign bit gets set, because 128 is required to get 144, the next Fibonacci number after 89. And at that point, the program will reset and go through again from 0 to 89, the Fibonacci series. So let's take this program, which I've compiled in a hex in parentheses off to the right of each instruction, and let's enter it into memory and then step through it on the computer.
Okay, so in this next step, we're going to input the program into memory. First by resetting the computer, setting all the registers and counters to 0, and then going into program mode. And then we're going to input the bytes for the instructions and their arguments into the appropriate memory locations. So first, in the 0 position, which we can see we're in address 0 on the yellow address register readout here, and then we can see we have a value of 0. We need to put a hex 1-1 for load A register immediate with a value of 1. So we put in here hex 1-1 and we press the right button, and that goes in the first index in memory. Then next, in memory index 1, we're going to need to put a store A command, which is hex 03. So we input 0 and then 3, binary on the second 4, and the memory index after that, memory index 2, is a pointer to the location where we're going to store that 3. Now for this program I've chosen to start my variables in memory at address hex 80, just because it's nice and out of the way. So I'm just going to put an 80 in there, and then we'll go to the next instruction. In address 3, we're going to be loading A immediate, a value of 0. So we're going to put in a hex 10, and put that in like that. And then the next instruction, we're going to be storing that value in another random memory location I'm using for a variable. I'm going to use hex 81, so we're going to put a store A command, which is a hex 03, and then in the next index, memory index 5, we're looking to put where it's going to go, which I just said would be hex address 81. And then after that, in memory index 6, we're going to put our output command, our output A register command specifically, which is hex E0. So I put in an E there, the first 4 bits, and a 0 in the second 4. And then in memory address 7, we're going to put in an add instruction. And this add instruction is going to be adding the value from whatever pointer I give it to a variable in memory. So we're going to put 20 for add, and then input in address 8 a pointer to the first variable, which was hex 80. In address 9, I'm going to take that value and we're going to store it in the location of the first variable. So we're going to put a store command, hex 03. And then after that, we're going to put a pointer to the location of the first variable. So memory address 10, we're going to put hex 80. Next, we're going to put a subtract instruction in address 0B11, and subtract is 30. And this takes an argument of a pointer to the memory location that we're going to subtract the value of. So then in address C12, we're going to put the location of the second variable, which is hex 81. And then after that, we're going to put in location D the command to store A, which is 03, and then a pointer to where we want to store it, which is the second variable in the next address, 0E, which is going to be hex 81. And then after that, we're going to put our jump less than 0 instruction, which is hex 61, and that takes an argument of a pointer to the location in memory that it's going to begin execution at. So then in address 16, hex 10, we're going to put the pointer right there. So we're jumping less than 0, which means we've hit the end of the program and we want to reset. So we're going to go right back to address 0, which hit the button anyway, but it's already in memory as a 0. Then in address hex 11, we're going to be putting the unconditional jump, just a jump instruction, 60. And this is going to go back and get the next Fibonacci number, or rather output the next one that we've already calculated. So this is going to want to be the address of the output instruction, which was the E0 instruction, which is in memory location 6. So we're just going to put a 6 here. And then for good measure, I'm going to add a halt instruction at the very end, just in case things go awry. We want to be prepared for that scenario. So here, the 6. and I'm just going to put a halt instruction there. So if we halt, we know that the program didn't run correctly. Now, before we are done programming this, we should go back through and check our instruction bytes against our reference sheet. So we're just going to go through the memory addresses, make sure we have the right value. So 0 we have 0x11, 2 we have 0x03, sorry, 1 we have 0x03, 2 we have 0x80, 3 0x10, 4.
I think you want to hear the song Wanted Zeros?
Alexa, never mind. Technology. In address 4, we're going to want to store a command, OX03. Address 5, the pointer, OX81. Address 6, the output A, OXE0. Address 7, the add, OX20. Address 8, the pointer to the first variable, OX80. Address 9, store a command, OX03. Address 10, the pointer, OX80. Address 11, subtract command, OX30. Address 12, the pointer, OX81.
Sorry, I'm not sure.
Alexa, stop. We're just going to mute the mic on Alexa now. Address, where were we? Yes. Address 12, we want the pointer OX81. Address 13, we want to store a command OX03. Address 14, the pointer OX81. Address 15, conditional jump less than 0, OX61. Address 16, pointer to 0 location, so 0. Address 17, unconditional jump, OX60. Address 18, the location of the output instruction, OX06. And the next after that, halt just for good measure in case the program goes awry. Okay, so next we're going to want to step through this program in memory. So we're just going to reset everything, counters and all the registers. And I'm going to start execution. So the very first thing that's going to happen is the fetch cycle, where we get the next instruction from memory and put it into the instruction register. So the very first thing we're going to do is we're going to take memory in and the counter out. Right now the counter is 0 and there's already a 0 in the memory address register, but the counter's coming out onto the bus and it's going to be loaded into the memory address register on the next clock cycle. Nothing exciting here. And we just advance to the next T state, where we're going to take the RAM out onto the bus into the instruction register, and we're going to enable the counter, so this is going to increment by 1. So now we're done the fetch cycle, and we're actually executing the load immediate A register value of 1. So we're taking now the instruction register out and the B and the A register in. And we just take the least significant 4 bits of the instruction register out onto the bus, so we have a value of 1, and then that's going to go into the A register on the next clock cycle. Now next, we are executing a fetch cycle because we did an early termination. So we're going to fetch from the counter that value 1, get it in the memory address register. Then we're going to get the next instruction, which is an OX03 for a store A into the instruction register. Now we're executing the store A instruction for real. And the store A instruction needs to get a pointer to the location in memory where it's going to store A. So the first thing it does is fetch the next location in memory to use as a pointer. So we say counter out and memory address register in and go to 2. And now we have this pointer, the OX80 I said we were going to use for the first variable. And then we take the memory address register in, the RAM out. So this value is going to go out into the bus and into the memory address register. And now we're looking at the location OX80 in memory, and we're going to put the value 1 from the A register into that, and then we're going to early terminate. You can see that already happened because I have it on the negative clock edge, sorry, the positive clock edge, but it's like level sensitive to the clock and it triggers on that one. Then the early terminate is the next instruction, and we're back to a fetch cycle for the next action. So now we're doing a fetch cycle, memory in, counter out. We're going to go to address 3 and get the next instruction, which is a OX10 for a load A immediate value of 0. So what that's going to do is it's going to say instruction register out, puts a 0 on the bus, A register in, and it's going to put 0 in the A register. And then we're doing a fetch cycle again, and we're going to get the next instruction, which is OX03 for a store A. which, as we said previously, is going to get a pointer to the location in memory where it's going to store the value held in the A register. So we get that pointer, OX81, and we're going to take this out into the bus back in the memory address register. Now we're looking at the location in memory OX81 where we can see we have a value of 0 from the A register. Remember how I said that that executes on that clock cycle, not when I press the button after the fact. So the next thing that's going to happen is the early termination. And now we're back to a fetch cycle for the next instruction. So we're going to take this 6 from the counter, output it onto the bus, get it in the memory address register, fetch the instruction, the OXE0 for output. That's going to go into the instruction register. Now we're executing the output instruction, which is simply going to take the value from A, output it to the bus, which is 0, so not very exciting, and then take it into the output register here, where we're going to be able to see its output on the display, which is, again, a 0. So we don't see anything remotely interesting that time. Now we execute another fetch cycle, and we're going to fetch that value, OX20, for addition, addition by pointer. So this is going to fetch the next memory location and use that as a pointer to the location in memory where we're going to take that value and add it to what's in the A register. So OX80 goes in memory address register. Now we have this 1 in that location, which is going to go to the B register to be added to A and then into the B register after that. So we can see it go to the B register. We got all kinds of fancy blue lights telling the ALU what to do, and it's going to do addition here. We can see that output here and on the bus, and then that's going to come out back into the A register. And then we're done. We're fetching the next instruction, which is a store A command, and that's going to fetch the next byte, OX80, for pointer memory. We go there, and we could see we took the value of the A register, and we stored it in that location, OX80. Now we fetch the next instruction, which is subtraction. So we're doing computation to go backwards to get the other Fibonacci value. If we just did the addition to get the next one, we're doing subtraction to get the previous again. So we're doing subtraction, which is going to go into the instruction register. Then this is subtraction by pointer, so it's going to get the next memory address byte, OX81. Take that, put it in the memory address register. Now we take that value 0. It's going to go to the B register, get subtracted from A, and get put into the A register. So watch that 0 go there. We're doing a subtraction operation with lots of fancy blue lights. And 1 minus 0 is 1. We see that result there and on the bus, and it's going to go in A now. Now we're back to doing a fetch cycle. We're going to get the next instruction, which is a store A command. We're going to get the pointer to where that's going to store it, the second variable, OX81, and that's going to go into the memory address register real quick here. And then we're looking at that value there, which was a 1, that we just took from the A register and put in that second variable. So now we hold a 1 and a 1, and we're going to get to our conditional jump instructions. We see jump less than 0 here in memory index OXF. Now we're not less than 0, so as we can see we have the flags, which are sign flag, carry flag, and 0 flag, and the 0 flag is off, so we're not going to jump. We're just going to go right through this, fetch the location where we would have jumped to, do a conditional jump, but we can see our jump LED, which is inverted, is still on, so we're not jumping. Keep going through, fetch cycle for the next instruction, OX60 for unconditional jump, so we're going to jump no matter what. This fetches the next location in memory. It's using this as a pointer to decide where to continue execution. So this value here is going to go ram out onto the bus. We can see the jump signal is high, so this is going to go into the counter, and the counter is also enabled. So here we go. Boom, we've jumped to address 60, and we're going to take from the counter now, memory and counter out on the next fetch cycle because we reset. And we fetch that instruction, which again was OXE0 for output A. Except this time it's a bit more exciting because we have a 1 in the A register, which just went in here into the output register, and now we see a 1 on the display. So this process just keeps repeating, and we calculate the Fibonacci numbers like this. So I go through it slow, and we do the addition, we got the 2, we store A, we do the subtraction, we got the 1 again, we store it, and then we're going to do not the conditional jump, but the unconditional jump back to the output instruction, where we had another 1. We repeat this process, we do the addition, we get a 3, we do the subtraction, we get a 2, we store that, and then we're coming around again and we output the 2. So if we speed this process up a bit, go by the automatic clock, and we'll just increase the speed so it goes at a reasonable pace but we can still see it. We can watch it do its job where we just computed the 5, we did the subtraction, compute the 3. Now on the next time around through the output instruction we're going to get the 3 out. You can see that just then. Then Did some more math. See, this time we got an 8 in binary. We did the subtraction, we got the 5 back. This time when we come around the 5, it's going to get output. And this process just keeps repeating for quite a bit while we go through all the positives. So now we're at 55. And we compute the 89, and now I'll halt it. And you can see also, and this time around, we've computed the 144, but 144 sets the sign bit, the most significant bit here, so the sign flag comes on true. So this time, when we hit the memory address, and I'll see if we can still get to it, we're storing A, and then we store that value, and this is our subtraction. We do the subtraction, store that value. And now we have our jump less than 0 instruction. So we're going to get this instruction in the instruction register. So now we have the instruction in the instruction register. We are executing the jump 0 instruction. It needs to fetch the pointer to the location in memory where we're going to jump. Okay, so it's got that. And you can see we just jumped because we had the jump less than 0 thing. Jump less than 0 signal was true, and you saw the jump LED go off, and then we jumped to that memory location. And now we're starting the program again. So remember the first couple things we did were load a 0, load a 1 in there, save that value, load a 0 in A, save that value, and then the program executes as normal, and we go through the Fibonacci series. So that's about all there is to it as far as program execution for the Fibonacci series program that I wrote. You may notice 2 new LEDs and another chip up here in the right hand corner. I actually noticed that I forgot to add a multiplexer circuit to calculate the carry flag on the bit shift ROM's operation. So it's just multiplexed with control signals from L2, L1, L0, which control the bit shift operation, and based on those it selects what value it's getting the carry from. For example, if we're shifting left, then it takes it from the most significant bit. If we're shifting right, it takes it from the least significant bit, and if we're not shifting, it takes it right from the ALU. So that's about it for this video. In future videos, I was looking to write a couple other cool programs and step through them also. Specifically looking to write a program to multiply 2 numbers, divide 2 numbers, do modulo, maybe even modulo exponentiation, some fast square roots by bit shifting, and then a program to validate prime numbers, one to calculate them by the sieve of Aristophanes. Since there's only 54 that lie on 0 to 255, I think we can fit that whole array structure into memory, and that would be a neat way to do it along with modulo. Also directly validating them by computation, so we could use the fast square root, then modulo, and just iterate through all the numbers from 0 to 255 and check them for primality that way. Would be another cool program. I'm open to other suggestions, so if you have any cool ideas, feel free to leave them in the comments, and I'll see if we can make it run on this monstrosity of a modern computer. Well, that's about it. If you like this video, you know what to do. If you didn't, I mean, I guess you can go ahead and do that. And otherwise, consider subscribing to see the rest of the series, and that's it.